we're now ready to move on to the next layer, which is the network layer. As a brief overview, we're going to split the network layer into two planes. One is called the data plane, one is the control plane. We'll go over more of the data plane in this series of videos, and the control plane will be left for the next week. In addition, we're looking at what's inside a router and IP protocol, internet protocol. That includes the datagram format, which is what we send through the network layer, fragmentation, IPv4 and IPv6, and network address translation. So how does the network layer work? Well, the network layer transports segments from the sender to the receiver. It encapsulates these segments into datagrams. The terminology here can get a little bit finicky. We were calling UDP segments datagrams as well. So for this, we're specifically referring to IP datagrams as what the network layer is packaging and sending along the way. On the receiving side, the network layer delivers the segments that it receives to the transport layer, which then, of course, delivers it to the application layer. Every host and every router is going to have the network layer involved with it, and the routers are going to examine header fields in these IP datagrams as they pass through. Now, the network layer has two key functions. These are forwarding and routing. So forwarding is where we take packets from the router's input to the appropriate router output. So you can think of it as if you're going on a trip, getting through a single interchange. Routing, on the other hand, is managed by the control plane. So this is where you determine the route that packets should take from the source to their destination. So this is the idea of actually planning your trip from your source to your destination. Now, one question is, what is the service model for the channel that transports datagrams from the sender to the receiver? And there's a few different services that might be available to you. For instance, for individual datagrams, you have guaranteed delivery, or maybe guaranteed delivery with less than a certain amount of delay. For a flow of datagrams, you may have a guarantee of them arriving in order, guaranteed minimum bandwidth, restrictions on changes in interpacket spacing, and so on. Here's a look at a few network layer service models. The network architecture might range from the internet or maybe an ATM. Service models include best effort, constant bitrate, variable bitrate, available bitrate, unspecified bitrate, and each of these vary in what they guarantee across the network. So the best effort model for the internet has no guarantees of bandwidth loss, order timing, or really anything, and there's no congestion feedback either. It's inferred via loss. Meanwhile, for an ATM network, constant bit rate may guarantee a constant rate, variable a guaranteed rate, available has a guaranteed minimum, and unspecified may have no guarantee of bandwidth. And each of these also varies with regards to their whether or not packets can be lost, if the order is right, or what the timing will be, and also the feedback of their congestion. Let's take a look at what's inside a router. As a general high-level view of what router architecture looks like, we have the high-speed switching fabric on the bottom here and the routing processor on top. So the processor is the control plane part of the router. It's the one that manages how to know where things should be sent. And on the bottom here is the hardware side of things, which is the data plane, the forwarding part that operates in a nanosecond time frame, much, much faster than the millisecond time frame of the processor itself. And so you can see the processor is going to have to manage the input ports and the output ports with regards to making sure things get sent to the right places. Now, how does a router know where to send the segments that it has? One approach is using destination-based forwarding. So we look at the destination address, we figure out which range our forwarding table has asked us to look up, and we associate it with a specific link interface. So any address that belongs in this range from this number here to this number here should go to interface number 0. And then so far for this range, which goes to 1, this range goes to 2, and otherwise everything else goes through interface 3. But now what happens if these ranges don't divide up super nicely? Well, another approach is to use longest prefix matching. So the idea here is that you, when looking for the forwarding table entry for a given destination address, you use the longest prefix that matches the address. So here is our destination address range. We have these prefixes here. These are the numbers you can actually see, and then everything with the asterisks is, this could be anything, whatever values it happens to be. Here's a couple of values at the bottom. Which interface do these belong to? So the first one you can see in the third series of numbers has 0010. So it only matches this prefix, meaning it has to go to link interface number 0. What about the second one? Well, you can see the second one has 00011, so it could match either 1 or 2. We use longest prefix matching to mean that we're not going to send it number 2 because it actually happens to match the 000 as well. So this is a longer prefix match, which means we're going to send this second example over to link interface 1. Now, how does longest prefixing work in practice? It needs to be done really fast. This isn't something that you can afford to even take milliseconds of time. It needs to be pretty much instantaneous. So longest prefix matching is often performed using ternary content addressable memories, or TCAMs. So the idea here is that it's content addressable, which means you give an address to the TCAM, and within one clock cycle, no matter how big the table size is, you can immediately retrieve the address that you're looking for. One example is a Cisco Catalyst switch, which can have look up 1 million routing table entries in their TCAM in a single clock cycle. Let's start delving into IP, Internet Protocol. So as a reminder, the network layer lies between the transport and link layers in our hierarchy, and it includes a number of different protocols that we need to consider. So first off, we have our routing protocols. This refers to the path selection, the way that we actually send our information, what way is it supposed to go. IP protocol, which handles the format of our datagrams, what are the conventions we should have for addresses and how to handle packets. And ICMP protocol, which handles router signaling and error reporting. Let's take a look at the format of an IPv4 datagram. So it's going to be 32 bits from left to right. First off, we have the IP protocol version number. So we're working with version 4 here, but version 6 is also out. Next, we have the header length in bytes, how long that happens to be, what type of data this is referring to. We have time to live, which is the maximum number of hops we can go from one router to another to actually get our datagram from the sender to receiver. We have the upper layer protocol that this payload is being actually delivered to. We have the total length of this datagram in bytes. We have a 16-bit identifier, flags, and the fragment offset, all of which are used to actually reassemble everything. So when your packets are all when they all arrive at the destination, making sure you can actually put everything back together. We have options which could include the timestamp, record the route that we took to get where, like which routers we had to visit on our destination. And this whole thing has an overhead of 20 bytes of TCP, 20 bytes of IP, so a total of 40 bytes plus whatever overhead comes from the application layer. Let's start digging into IPv4 addressing. So as a brief introduction, an IP address is a 32-bit identifier for a host or for a router interface. And an interface is just a connection between a host or a router and the physical link. So most routers will have multiple interfaces. You can see that this one has 3 here. Each one has its own different IP address. And a host typically has 1 or 2 interfaces. You might have one for wired Ethernet, another one for Wi-Fi. And each interface is associated with a single IP address. And it might look like something like this. So we have 223.1.1.1. So this is 8 bits separated between each point. So 8 bits, 8 bits, 8 bits, 8 bits, hence 32 total. And if you were to literally write this out as bits, that's how you end up with 110, 111, 11, and the 1, 1, and 1. And that's where all the numbers come from. So IPv4 addresses are split into 2 parts. One is the subnet part and one is the host part. The subnet part are the high order bits, meaning the ones on the left, and the host part are the low order bits, the ones on the right. What is a subnet? Well, a subnet is basically the part of an address that you can reach without actually going through a router. So you can see here that this network that has one router here has 3 subnets, each attached to it through a different interface. So the device interface, a device can interface through the same subnet parts, like this host over here, 223.1.3.2, can contact 223.1.3.1 in the same subnet without having to actually go through the router. So here's a pop quiz. How many subnets are there in this picture? Well, conveniently, we've actually highlighted them all for you, but it may not seem obvious. However, these connections between the routers also count as their own subnets. Essentially, because you are able to connect between this interface of this router and this one without having to go through a router, this part here is a single subnet, which means this one is as well, this one is as well, and we obviously have the subnets of hosts on the outside, meaning there's a total of 6 subnets in this diagram. Now, how do we know which bits denote the subnet part and which bits denote the hosts? One way to do this is using CIDR, which stands for Classless Interdomain Routing. And the way that this works is that the subnet portion of the address can have any arbitrary length, basically up to 32 bits. And the address format looks something like number.number.number.number/x, and x is the number of bits that are in the subnet portion of the address. So you might see something like this here, where the IP address is 200.23.16.0/23. And what this means is that the first 23 bits here refer to the subnet, and the remaining bits, which there are 9 left, 8 plus 1, refer to the host. Now, how do you get an IP address? How does a host actually have one? There's 2 ways you can do that. One is if it's hard-coded by the system administrator in a file, so you go Windows, Control Panel, Network Config, TCP/IP properties, or in Unix you can go to /etc/rc.config and actually set the IP address manually. Alternatively, you can look at DHCP, or Dynamic Host Configuration Protocol. And the way this works is that you dynamically get an address from a server. So you plug everything in, and then an address is given to you. That's the address that you use. Now, most of the time you'll rely on DHCP to get a dynamic IP address from the network when you're joining the network. That way you can renew your lease on the address while you're using it, allow you to reuse addresses and only hold them when you're actually connected, and you can release them when you're not needed. And it allows support for mobile users who want to join the network later. Here's a scenario of a new client arriving in a network and needing a new IP address. So our client here shows up and says to our DHCP server, hey, is there a DHCP server out there that can give me an address? So it sends the message, the DHCP server replies and says, I'm a DHCP server, here is an address you can use, and it gives the address 223.124. The client then replies and says, oh, okay, I will take that address, here is the address I have taken, and then the server replies and says, okay, that IP address is yours. And so among all these numbers, a few stand out. You can see a 67 and a 68 here. These refer to the port numbers that are specifically for DHCP. And then YI address is the address that you actually are giving to the arriving client. Now, DHCP can do more than just dole out IP addresses. We can also give the address of the first hop router for the client so it can figure out where it should start sending its messages. Provide the name and IP address of a DNS server if you need to get on the internet, and also provide a network mask, which allows you to indicate which part of an IP address is the network versus which part is the host. Now, the benefit of hierarchical addressing is the ability to quickly advertise routing information so you can access the networks you need to access. So here we have a few different ISPs. We have Fly-by-Night ISP and ISPs RS. And each one tells the internet that they are going to be responsible for a certain block of IP addresses. So ISPs RS is going to handle any IP addresses that start with 199.31.0.0/16, while Fly-by-Night ISP will take anything starting from 200.23.16.0/20. And so if there are organizations that are handled by their Fly-by-Night ISP, each one, this first one is 200.23.16.0. It's the first one that has these first digits, or 200.23.18, 2320, so on up to 2330. All of these are in the same block of addresses that this ISP is maintaining, so it should be the point of address if you're trying to contact it through the internet. Now, how does an ISP get a block of addresses? And the way it does is something called ICANN, or the Internet Corporation for Assigned Names and Numbers, and you can check out the website here if you want to. This is the administration for allocating addresses, managing the domain names servers, and assigning domain names, resolving disputes. Let's take a dive into network address translation. So here we have a subnet. The subnet address is 10.0.0/24, so the first three sets of 8 bits are all 10.0.0. And so datagrams with source or destination in this network have 10.0.0/24 as their address for source destination. All datagrams that leave the local network have the same source IP address, which is the 138.76.29.7 that comes from the interface of this router. So the rest of the internet is just going to see this address, not the ones that are inside here. So what's the benefit of this system? Well, this way, the local network is just using one IP address, and the rest of the world associates the network with that IP address. By doing so, the range of addresses that are available are not needed from the ISP. Just one IP address will do. It also means that you can change the addresses of devices in the local network without notifying the outside world when this happens. You can change the ISP without changing the addresses of the devices in the local network, and devices inside the local net are not explicitly addressable or visible by the outside world, which is really good for security. If you have a system on your network at home and you don't want people outside to be able to access it, it's definitely a lot better to not be visible than to be visible and have some other layer of protection. Now, a router that handles network address translation has a lot of work to do. First off, the router has to replace source addresses and source IP addresses and port numbers of outgoing datagrams to the network address translation IP address and a new port number. Remote clients and servers then respond using that new NAT IP address and new port number as their destination. So they're not talking directly to the host that sent the message. Like, the host IP address is not going to be known to the remote client. They're going to be essentially referring to the router. The router also has to remember in a translation table every pair of source IP address and port numbers to what it has translated everything to. So the new network address translation IP address and new port number needs to have some record to match it with the original source and the original port number. For incoming datagrams, the router has to replace the IP address and new port number in the destination fields with the corresponding data that's stored in the translation table. Let's go through the process of network address translation from one step all the way to the end. So first off, let's have our host 10.0.0.1 sending a datagram to this address and this port number. It arrives at the router, and to the translation table, we add the pair of the original data that we have to the new address, which refers to the router's interface address, which is the number that you can see over here. The destination port is still the same, and there is a new port number here, 5001, that's added to make sure that the router can connect this 5001 number here to the 3345 that indicates this host number from the router's subnet. Then for the third step, a reply comes from the destination, and the address this time is the router address right here with this new port number 5001. And so the information from that needs to be looked up on this table, which translates this pair of numbers here into the original values that it needed to be to make sure that the router can forward the message, the datagram, from the destination to the host that had sent the message in the first place. Now, a few more notes about network address translation. First off, the port number field is 16 bits, so that's 60,000 potential simultaneous connections with a single LAN side address. NAT itself is controversial in a sense. that routers presumably should only process up to the network layer. And this issue of address shortages that we have, now that there are so many devices and IPv4 only has so many addresses that we can use, the reason that NAT is so controversial is that IPv6 is proposed as a better solution to the fact that we have more hosts than available addresses. In addition, NAT violates the end-to-end agreement. The possibility of this address translation now needs to be something that has to be taken into account by app designers, so those working at the application layer now have to consider what's going on at the network layer, which is not a great thing. So something like a P2P application has to consider address translation as part of a problem now. For technical solutions to this problem, you can try looking up NAT traversal if you're more interested in this problem. So I've mentioned IPv6 a few times already. Let's talk a bit about what that is. So IPv6 was originally designed because the 32-bit address space of IPv4 is soon to be completely allocated. There are so many devices out there at this point that limiting ourselves to this small address space is a problem. So IPv6 gives us more space that we can allocate these addresses for. In addition, the header format of IPv6 helps speed along processing and forwarding, and the changes better facilitate quality of service. So IPv6's datagram format is a fixed 40-byte header with no fragmentation allowed. Let's break down what an IPv6 datagram looks like. So here's the general format over at the bottom. A few things we can note are PRI is the priority, so this is a priority among a bunch of datagrams in a flow. A flow is kind of like a group of datagrams that are all associated together. There's no real strict definition to how this works, but the flow label here is intended to help you associate different datagrams with each other if they're from the same flow or the same group, kind of. The next header also here identifies the upper layer protocol for the data. A few other changes of IPv6 from IPv4 include, first off, the checksum being removed entirely to reduce processing time, options being allowed but being removed from the header indicated by the next header field, and ICMP v6, which is a new version of ICMP that has additional message types, for example, packet too big, and has no fragmentation in intermediate routers. So this means that the sender will receive a message that says the packet is too big and be forced to resend datagrams of a smaller size. Now, an obvious problem of transitioning from IPv4 to IPv6 is that it's not really possible to just upgrade all the routers at the same time. There's no flag day where we just decide, all right, we're switching off all the IPv4s and everything is IPv6 now. Which brings us to the question of how can you have a network operate where some of the routers are using IPv4 and others are using IPv6, or some are using both. The way this is done is use something called tunneling, where an IPv6 datagram is carried as a payload as the data part of an IPv4 datagram among routers that can only handle IPv4. So here we can have an IPv4 datagram where it has its header field, source, destination address, and so on. And this blue section here is the payload, but that payload can be an IPv6 datagram, which has its own header fields, its own source, destination address, and payload as well. So a datagram inside of a datagram. Let's take a look at what tunneling looks like, both from a physical and a logical point of view. So physically speaking, we might have 6 connected routers building a string that takes us from our source booked somewhere around router A and our destination around router F. Now, A and B and E and F are IPv6 routers, whereas C and D are IPv4. So what happens is that, from a logical point of view, there is an IPv4 tunnel comprised of C and D that connect to the IPv6 routers B and E. So if I'm starting from A and I have a datagram, it's an IPv6 datagram, and I want to send it all the way to F. My source is A, my destination is F, it has some flow number, and there's data contained in it. Now, to get all the way to F, I need to go through this tunnel. So that means that once my datagram arrives at B, it needs to encapsulate this datagram, the IPv6 one, inside an IPv4 datagram, which is the red box. And so you'll see that the destination here and source are different. The source of the IPv4 datagram is labeled as B, and the destination is E. That's where the tunnel ends. So as it goes to the tunnel, it arrives at E, and then the IPv6 datagram inside is extracted and then sent from E to F. And at this point, the source is back to being labeled as A again, because that's where it originally came from, and the destination is correctly labeled as F. That's where we want to end up. Now, how is IPv6 actually doing right now? Statistically, Google has about 8% of its clients accessing service via IPv6. So, you do the math, that's not most of them. And 1/3 of all US government domains are IPv6 capable. So, once again, not most of them. And this is a thing that's slow in coming. At this point, it's 2020, so it's 25 years since IPv6 was actually originally introduced. And, think about what's happened in the last 25 years. I imagine a fair number of people watching this video were not around back then. So it's pretty crazy to think about how this idea of having addresses that are long enough to maintain the number of hosts that we have has been around for so long that we still haven't actually been able to put it into practice everywhere that maybe it should be. So that was a quick overview of the network layer's data plane. We talked a bit about what's in a router, what does a router have to do, forwarding and routing, IP, internet protocol, all the things that go into that, begging the question, how do the forwarding tables, so for destination-based forwarding, or flow tables for generalized forwarding, how do we compute that? And the answer is through the control plane, and that's going to be the next thing that we'll talk about after this video.